Hello everybody. Um, Here's my. I'm still stuck on 5-4Q after so many days and I haven't made recordings. Partly because I'm actually, tell the truth, embarrassed. I keep coming up with solutions that almost work and then they fail. And so let me dive into what I've got now, which I think is going to be proper. So I'm not gonna even go through the failed ideas because there doesn't seem to be much point. So here's a new idea, and it makes a lot of sense. I think it'll work. So first of all, these are the things I want to accomplish. Number one thing I need to do is I need the ability to commit the queue to the database, or commit to the file system, which means that if we lose power or crash, then we still have a working, we still have a copy of what the queue looked like beforehand. I need this because for Whiteboard, the way it works is that I need there's like a list of nodes, in the whole DAG, directed asymmetrical graph, and these nodes are like the current state of what's been calculated or what needs to be calculated that's left. So if we do some partial calculations, or then we have maybe another set of nodes that need to be calculated, and we're kind of like working with the database, working with the file system and so forth, and so this isn't really completely written to the file system, so maybe this is still in transient data. It's okay if the system loses power, because we can just recompute that from the original set. So as long as we have a FIFO-Q that can perform this commit, we're okay. So that's number one. That's really all I really need for the first version of this. But I just thought, because we're storing things to disk anyway, I might as well make it so we can have an infinite, or basically a disk-bound FIFO-Q. So the FIFO-Q can live partially in memory, and partially on the disk. So basically how that works is that you might have like the read end here, you're starting to read the elements and kind of pulling them off. Then you have this big center part that's stored into the file system, and then you have the right end here. And the right end is just continually adding elements to the end. And so then there's a thread here in the middle that keeps looking at these two queues and what's in the disk. And it's called a disk thread. And so what it will do is that if this queue, this read queue, becomes too small, so it becomes like maybe one or two elements, then it's going to go to the disk and it's going to fill it up. And then the write queue also, if it becomes too large, it'll go and write it to the disk and then start over with a brand new empty queue. And then also, if the queue becomes so short, which normally it should, that it can all fit into memory, I mean this is pretty much a basic case, which it's almost always going to do, then the disk thread won't do anything. And basically there's, I'm not sure a disk there, but it's not a disk, it's a thread. So the disk thread basically just let the write queue kind of dump its information into the read queue. And there's another restriction that I want, number two. Well, this is kind of like number two actually. The fact that it's an infinite or a disk-bound queue, or basically it can be the size of the disk space and not just the memory space. And number three, number three is that I want it so that if the queue is in this situation where the read queue and the write queue are in memory and there's nothing on the disk, that when we commit, because basically we're going to save off, when we commit, even in this situation we still need to go to disk. We need to save off the read queue and the write queue to disk, so that later if the system crashes, we can return the state. So I want also to happen is that in the case where it's doing this, that it doesn't really affect the performance of the queue. In other words, the queue can still continue to move and go on while we're saving an old copy of how it originally looked. So that means that if something's in memory, we have to keep it in memory and not drop it, even if we put it to the disk. And then, of course, the fourth thing is we have to do this because we have like this last committed data, which is the last journal or last commit. And then we also kind of add to it the rows for the current commit. So if you imagine it looking like this, like there's a bunch of files here for the last commit, maybe 1, 2, or 3 files for the last commit. And the current commit starts out exactly the same as the last commit. These are the files that are on the disk that we care about. Then as we process the queue, the current commit kind of grows. So there might be, the 3 original files. This is the last commit. And then there might be additional files. And then the current commit may still overlap the last commit, but might have additional files here. And also might have a particular starting point. Like maybe the read queue read through like half of the file, so then the new commit has like a certain starting point here. So, let's see. What am I thinking? I forgot what point 4 was. Okay, so we have the last commit. Yeah, so it has to handle this. It has to handle this kind of situation, and I don't want to have to like copy data everywhere. Like I don't want to say, okay, well I have one current commit and then the last commit, and we just kind of copy the data across to new files, because it's just, I don't know. I wanted to be able to handle like huge amounts of data without having to copy things or do things that would take longer than just read individual elements. So yeah, I mean, I don't know, maybe I'm just too hard on myself, but I'm making this into a system that can perform very well even with large amounts of data. Because I guess the thing is, like, I don't know, tasks that I'm currently working with won't have so many rows in this thing, because these are basically going to be tasks to run. So when Whiteboard, I mean, it depends on what you use Whiteboard for, but I mean, for the tasks I'm going to use Whiteboard for, which are basically, I'm thinking of a Nix REPL, and also, of course, NumBitcoin. I don't think this is going to grow that big. It could, but I doubt it. But I'm not sure, and I kind of wanted to make a generic and very powerful system that anyone could use for conceivably any task. And then the idea, I mean, just to reiterate, the idea of Whiteboard is that it can handle multiple threads, and it can handle, data that's larger than what can be held in memory. And just basic performance calculation. And so, like I said, it's like a calc base. So the idea is that you have outside data that might be continual changes, and might be continually changing, and you store it, however you store it, and then it goes into, and so Whiteboard just reads that. So I keep drawing disks. So Whiteboard just reads this outside data and then comes up with these calculations that can then that also be stored on disk. Oh, the other thing is that it also is it can be partially run and then shut down or crash and then pick up where it left off. So it has like a permanence. So then the files or whatever input data then goes into Whiteboard and does these calculations, and it might take a long time. Like if it's a blockchain, let's say it's going through possibly hundreds of gigabytes of data, it's going to take a long time. So you want it to be able to partially run and then finish, or if it's a large program or whatever. In the case of NumBitcoin, it's kind of both. It's a large program, and it's also a blockchain, so it's both. So for Nomic coin, it definitely needs something like this. I mean, I could create something specific to Nomic coin, but I figured, why not try to create something generic? So anyway, back to the problem at hand. So I need this queue, and I want to have all these features, even though I probably only really need one. I'm going to try to get 2, 3, and 4 as well. So this is the current way I'm doing this, is I have a read queue, and it will have a blah, 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 blah. It will have a, it's a start index. What is it start? All right. So let me back up a little bit. There's going to be, in most cases, except for when it's just for start, there's going to be a last commit, and that last commit is going to have one or more files. We assign 0 as an index to the first element in the first file. And so on disk, we'll have a basically a couple things. We'll have a start byte offset, which I was kind of describing before, that we need this because when we commit, we don't want to like rewrite a file that's already been written, so and if we read partially through a file, we just want the last part. So we have a start byte offset for that, and that just indicates where we're going to start reading from when it's in a committed state, which means there's nothing in memory. And then we have a count, which represents the total size of the last commit. And the reason we need that is because when we put into memory, we're going to have the read queue take like the first few elements and stick those into memory. And then the write queue needs to write at the end of this list, or whatever that's supposed to be. So it needs to know how many elements are in the queue, are in the disk. So then basically, when we go through, we start reading and writing, if the read pointer inside this list of files if it keeps like growing and growing and growing and ever gets to the point where the write queue is, then we know that there's no more disk data left, and then we can start moving the write queue data directly into the read queue when the read queue empties. And so this makes it go a lot faster because now it no longer has to go to the disk. So that's the first part. So we have this disk data with these operations, count and a start byte offset. So let's see. Then, in addition to that, then we have like what we call so that's the last commit. So the last commit is copied into another item called the current commit. And the current commit, like I was saying before, like we have a last commit and has some files, and then the current commit kind of overlaps it initially. And the current commit represents what file to go to, where it starts and where it ends. So as we start to read data from the disk into memory, we update the current commit, and we update a few things. We update the byte offset. If we read a partial file, actually we probably would never read a partial file, so I don't know if we really need this. But we also update the start index. Oh, actually, I understand what this is. Okay, so there's different indexes. There's item indexes and there's file indexes. So in the last commit, in addition to this, we also have like a file index start and a file index end, which just represents, like each of these things that have a name with a number attached to it. So it might be like data file 1 and data file 2, data file 3, and in that case, the start would be 1 and the end would be 3. I'd probably make it 4 to make it exclusive, but to say that it goes from 1 to 3 and 4 is too high. So the same thing with CC, which is a copy of LC. CC stands for the current commit, and LC stands for the last commit, or maybe like the current state, I don't know. But so this starts out the same as the other one, so it has the start file index and and file index, and again 1 and 4. And then what we do is, well, actually we'll need this because the last commit has a byte offset, and the reason we need that is because when we commit the rows, we need to sometimes we read half. I said this before, but sometimes read half queue and then read queue, and then the remaining amount we need to store into the, or specify where it is in the system. I think we might also need a byte offset in the read queue. Oh gosh, I was hoping we didn't need this, but I think we do. Alright, well, anyway, I'm just going to probably finish this quickly. I still have to think about some more things now. Let me just put a star here, byte offset, and read queue. Alright, so, now the thing is, we got all this, then what happens is then we have the read queue, and we have the thread, and it goes through and looks at the current commit, and it will read into the read queue, and then it will update this current state. So if it reads file 1, then it updates it to 2, and so on, and then, so this is the disk thread. So it basically performs just one operation at a time, and it's just one thread. So I did it that way, so I don't have to worry about contention between threads. Like I could have a read thread and a writer thread, but I just have one, because read disk access is just, I just think one thread should be enough. And then it just makes it easier. So then the disk thread will also, when it writes to a new file, it just updates here in the current state. It updates it from 4 to 5, and then it creates a new file 4, and so on and so on and so on. So that's how it handles reading and writing between the two. When we commit, we store the file, store the data to the file system. So we have. So if we're in the read state, if we already part of if the file system already contains what we're reading, then we just kind of just drop it and just keep track of it in the commit, that's the current state, which then becomes a new last commit. And then when we write in the write queue, we just dump. Well, we also check to see whether it's already in the file. If it is, we don't do anything. Otherwise, we dump the rest into a new file. And yeah, so alright, so that's the thing, is whenever we commit, we are after we commit, then we have this read queue, and then we have this write queue, and the write queue will say hey, I'm already in the file system up to this certain particular element, like a count, the number of elements that are still in the file system. So when we continue to write to it, and we do another commit, we know just to write from here on out. And then the read queue, it's kind of backwards, that it actually has a pointer into the file system. It says I have a particular byte offset, and then if we read through half the items, then we put a new byte offset into the file system. So this is why I just figured out now that the read queue also needs a byte offset in it. And alright, so that's the current plan. Yeah, I've been spending a lot of time on this. I didn't expect it to take so long and be so difficult. I was thinking of using there's something called data kinds, just to be able to make it less because right now for every step I need to go through several different variables and make sure that they're updated properly. So I wanted to see if I could find a way to make it so in the type system I could create some sort of constraints that would allow me to make sure that I update variables in a proper way. But it just seems too complicated. I think I'm adding too much complexity, and I really just have to get the system perfect in that it can do everything I want it to, using the least amount of variables and being as simple as possible. It's still pretty complex, but it's not. There's certain laws that reduce the complexity. For instance, there's a queue which has outside threads that read and write to it, And one thing about these outside threads is they never update data and that talks about the disk. So the threads that they read and write thread, they don't know anything about the disk. All they know is the starting read index, the starting write index, and whether there's a gap here, and they basically count, and that lets them know whether there's a gap here. If there's a gap, then it knows that it can't move the write queue into the read queue. And then the disk thread is going to read both of these elements to determine whether there is a gap or not, and then it knows whether it needs to start moving stuff from one to the other. And the other thing is, the one other condition that I wanted, step 5, is that when we commit, it has no effect on the queue. So if in the special condition where the read queue and the write queue are kind of joined here, I think I said this already, that it has no effect, so that these guys can still operate even while we're committing the data. And so that prevents the system from, anytime we commit, it's not going to like pause the system, it's going to just keep running as long as it can fit the thing in memory, which I think is pretty cool. And that's it. All right.